Good evening. It's a pleasure to welcome Subir to Math Science after a long time to give this Diamond Jubilee distinguished lecture. When I was asked to introduce him, I couldn't resist the temptation of going to ChatGPT and saying, introduce Subir Sachdev to a Math Science audience. It did a lousy job. So Subir is a professor in Harvard University, and he's been there since 2005. Before that, for a long time, he was in Yale. He has got, a lot of recognition and awards, including the Dirac Medal from New South Wales in 2015, the Dirac Medal from ICTP in 2018, the Lars von Sager Prize given by the APS in 2018. These are just a few, but now Subir started his research in the 80s. That's the decade in which there were two major discoveries in condensed matter, quantum Hall effect and high TC superconductivity. So that has shaped his work, as it has for many of us. And then there was a body of work that came from him on quantum critical systems, frustrated quantum antiferromagnets, mainly in 2+1 dimensions, and also on fractionalization of quantum numbers in correlated systems. And sorry. And then finally it led to a path-breaking idea of Subir and others of deconfined criticality, a class of phase transitions that did not obey the Landau paradigm. So a truly new kind of physics over there with explicit models. After that, the other, Subir has always, he has fantastic technical ability, and he has a very deep understanding of physics. So he's able to understand concepts on string theory, field theory, condensed matter physics, and put it all together. So apart from just, it's always fascinating where physics at one length scale is applied to physics at a different length scale. But apart from that, in today's topic, there's a genuinely new physics idea that comes out of it. That is of a metal without quasiparticles. 10 years ago, if you had asked me or any other condensed matter physics, do electrons have to organize themselves into weakly interacting quasiparticles? I would have said not necessary. Somebody tells me, then why do you always think that way? I would have said, I have no other way to think. So now there's a really genuinely new way to think about it. And let me invite Subir to tell us all about it.
Yeah, first of all, thank you, Shankar, for that very nice introduction with, really nice survey of my life, and I appreciate all the nice things you said about it. And also, it's an honor for me to be here on the Diamond Jubilee celebration. Okay, so the title, as you can see, involves topics from many different fields of physics, and you might rightly wonder what, if anything, these different things have to do with each other. And hopefully by the end of my talk, I'll answer that puzzling question, at least to some extent. And I promise you that I'm going to keep this fairly comprehensible, even if you don't have a background in quantum field theory or many-body physics. Let me just begin at the very basics, just remind you of some concepts which are really at the foundation of almost everything in quantum condensed matter theory and also rest of physics. And they both happen to be laid by Boltzmann already at a time when there was no quantum mechanics. Some of those principles are even deeper and more widely applicable than quantum mechanics itself. So one of them is, of course, the statistical interpretation of entropy. Prior to 1870, entropy was some quantity that you cooked up in thermodynamics that you could compute by measuring heat flows out of a body while you're making an engine or something like that. And then it was Boltzmann who first said, well, no, entropy is a statistical quantity, and it measures something about the microstate of the system. You have some many-body system, and what it's made up of, its constituents, which he postulated to be molecules whose existence had not yet been established. And there was something about the molecules that determines the entropy. And this famous formula, which is on his gravestone, says that the entropy is the Boltzmann constant times the logarithm of W, and W is basically the number of states available to the microscopic constituents for a given macroscopic state. Now, in quantum mechanics, we describe states by eigenstates of some Hamiltonian. So you have some many-body Hamiltonian, which has some eigenstates, and which have some eigenvalues. So just imagine for the many-body system, you could compute all the eigenvalues, which is essentially an impossible task. And even for the model I described, we can't do that. But sometimes you can nevertheless compute the density of states. So in some small energy interval, you can ask how many states are there. And so for quantum mechanics, that's a measure of the number of the number of eigenstates in a given energy interval is a good measure of W. So then you relate the density of states, d of E, to the exponential of the entropy. And that's the fundamental relation that will play an important role in everything I talk about today. The second innovation by Boltzmann is the Boltzmann equation, with which he understood properties of classical gases, like the gas in this room. So the picture here is you have some molecules which are behaving classically, obeying Newton's laws of equation. And Boltzmann wrote down the Newton's laws in terms of a distribution function of molecules at each momentum p. So that's the left-hand side of Boltzmann's equation. And these molecules, of course, if they never saw each other, there's no way you're going to reach thermal equilibrium. So they have to collide. And Boltzmann's innovation was to treat successive collision as statistically independent. So if you have one collision happening, it doesn't matter whether this particle collided with some other particle before. It's completely forgotten that. And once you make that assumption, then you can account for these collisions by this collision term on the right-hand side. So what are the various terms here? There's one term that conserves energy, another term that conserves momentum, and the other is simply saying that the probability that the two particles collide is proportional to the probability of the product of the probabilities of having a particle momentum p and having a particle momentum p1. And then there's the inverse process where the collision happens in the time reverse direction, which you have to subtract out. So this is it, and this is the classical Boltzmann equation. And if you solve this, of course, you get the Maxwell-Boltzmann distribution in equilibrium, but you can also do other things, like look at dynamical properties, how the gas will flow, compute its viscosity, and many other things. And all of that works beautifully, so this was another incredible success by Boltzmann in 1872. All right, so now we fast forward to our present century, or actually the previous century. When you have quantum mechanics, amazingly, the Boltzmann equation can also apply in quantum system, but not in some dilute classical limit, but in the dense quantum limit. So if you take a dense quantum gas of fermions, then you get essentially the same equation. The only thing here are these 1 minus f factors on the right-hand side. That's the main difference. And this is simply a statement of exclusion principle. So if these two particles are quantum particles colliding with each other, then the collision can only proceed if the final states are empty. If the final states were full, then you couldn't have this collision, so you have to put the 1 minus f factors here. On the classical limit, f is much smaller than 1, always, and so you can ignore these factors. But in the quantum limit, you can't. Now, but you again make the same assumption that successive collisions are statistically independent, not just in a thermal way, but also quantum mechanically. So you neglect any interference, or entanglement being the modern word, between successive collisions. Okay, so now the point is that this thing can still be small in a dense quantum gas, not because the collision cross-section is small, as is the case for dilute classical gas, but because these 1 minus f factors. So if you look at this factor, now in a quantum gas, like a free Fermi gas, each state is either occupied or empty. So if a particular state is occupied, then the f's are 1 and the 1 minus f's are 0. On the other hand, if the state is empty, then the f's are 0 and the 1 minus f's are 1. In any case, no matter what happens, the product of all of this is close to 0. So the only place there are any collisions that can proceed are right at the boundary where f changes from 1 to minus f, from 1 to 0, and that's where we have what's called the Fermi surface. So amazingly, both in a dilute classical gas and in a dense quantum gas, you have basically the same equation, and you can treat a many-body system as a collection of almost independent particles with rare collisions, or which we now call them quasiparticles. Okay. So that's the quasi-particle picture of a many-body system, in particular a metal. And that's the picture that has been incredibly successful in many-body quantum physics and condensed matter physics. So if you want to describe the flow of electrons in copper, you basically apply a Boltzmann equation. And if you solve the Boltzmann equation in the quantum regime, you get this basic result that the typical scattering time diverges as temperature goes to 0 as 1 over temperature squared. So this time becomes very long at low temperatures, but so as things become more quantum, the collisions become rarer and rarer, and the Boltzmann equation is more and more valid. And so from this you can compute, for example, the resistivity, which is some constant plus T squared, and this is precisely what you observe at low temperatures in a material like copper. Now you can ask, when can this break down? When are the collisions so frequent that you can't treat the particles as nearly independent except at collisions? And this, of course, will break down when the time becomes too short. So what is the lower bound on this tau? So you can kind of reason a bit more about this and wave your hands a bit using some uncertainty principle. And then you find that you get that there is a fundamental lower bound, which is h bar over the temperature measured in units of energy. So this is now what's often called the Planckian time. And if you had a metal where the tau was of order h bar over kt or even shorter, then you would believe that you can't apply the Boltzmann approach. And as I'll show you, that's in fact what's observed. There's also various arguments I will go into that this is the shortest possible time, that if you define any reasonable measure of some kind of equilibration time, it never becomes shorter than a time of order h bar over kt. Okay, so that was the situation, before 1980 and the great discoveries that Shankar mentioned. So this is a phase diagram of the cuprate superconductors, and it has superconductivity up to 100 Kelvin. Well, that's not my main interest in this talk today. But if you go in this region above the superconductivity, where you believe you should have a normal metal, as you do in the older superconductors, you find what's now called the strange metal, which is continuing to be studied, and many of its properties, both experimentally and theoretically, still a topic of great research interest. And one of its paradigmic properties is that if you look at how the resistance varies with temperature, as you come down in temperature over here, in copper, as I said, it should come down with a T squared. It comes down linearly. And this is present, for example, in lanthanum strontium copper oxide, which is a high temperature superconductor. This is the superconducting transition. But above Tc, it's a perfect linear function. And this is twisted bilayer graphene, which I won't say more about, where also you see linear behavior. And then there are ways in these experiments to also measure the collision time between the electrons. Again, I won't go into any details, but here's a recent paper by looking at what's called the angle-dependent magnetoresistance. So again, I'm going to skip a lot of details here, But if you look at this, let's see, I'm certainly confused. This is as a function of temperature. If you look at the isotropic component of the scattering time, which is this red line here, it goes linearly in temperature, as you might have expected from the resistivity already. But if you put the numbers in, it's in fact exactly very close to the Planckian time. So manifestly here we have a system where this Planckian time is showing up, and really the Boltzmann approach can't work. So we really cannot treat the collisions as independent. We cannot neglect the quantum interference between them. We need a whole different way of thinking about this many-body system where entanglement is happening on a much larger scale than would happen in an ordinary metal. Okay, so many-particle quantum entanglement from quantum interference between collisions has to be accounted for. All right, so of course these things have been well known to everybody, and many people have tried various approaches, which has taught us a lot. But today I'm going to begin by discussing a particular solvable model, which has really been very helpful in making many progress, I hope to convince you, which is called the SYK model. So this is something I came up with in the early 90s, precisely motivated by the experiments I've just discussed, or the earlier versions of them. At that point, I said, well, let me not try to actually understand the real world. I just want some model of interacting electrons where we can prove that there are no quasiparticles. And let's just try to understand it. Because almost any other model that people looked at before eventually had quasiparticles, including actually the fractional quantum Hall state. It has quasiparticles, but they're just complicated. So you want a model that has electrons in it, which you can vary the density of electrons at will, as you can in a metal, and yet has no quasiparticle-like description. Okay, so that's right. Okay, I've already said that. A solvable model of many-particle entanglement, which leads to a metal with no particle-like excitations. Okay, so let me just describe the model pictorially first. So let's just imagine that electrons can only sit on a given set of sites, which this is in position space, but it can be any other parameter space you like. So I have 18 positions here, and you occupy some fraction of them with electrons. So this is one possible state in my Hilbert space with these states occupied. And now I have some matrix elements, which will allow me to go from this state to other states, and then those matrix elements will define the Hamiltonian that whose eigenstates I have to figure out. This is not an eigenstate. Now, one thing I'm going to do here is force the electrons to really entangle with each other. If you take some generic set of matrix elements, you will get quasiparticles at low enough energies. And that's just a disappointing fact of life. But for now, let me imagine I prohibit the electrons to move individually. So all I'm going to say is that the electrons can only move in pairs. So for example, an electron can move from site 11 and 12, which are occupied, to sites 5 and 14, which are empty. And so this is one process that's allowed, and it has some complex number associated with it. There's a matrix element or a tunneling amplitude for this process to occur. So this is a number that you have to tell me, and then I can figure out the dynamics. Exactly where the electrons are and how they interact will determine the value of this number. All right, so there's a number there. But I can assign such a number for any such process, for example, from site 4 and 5 to site 11 and 18, and so on. So I give you a set of n to the 4th numbers, and I tell you to tell me the energy eigenstates of this particular model. That's a completely hopeless problem. If I had more than about 30 electrons, even the best computer in the world can't tell you what the energy eigenstates are, because the Hilbert space is so large. So this seems like completely hopeless for an arbitrary set of numbers characterizing some random distribution of electrons to determine every eigenstate. And it's true, you can't. But if I tell you that these numbers, these U numbers, are statistically independent of each other. They're like some random numbers you drew out of a box, which is almost any set of numbers, really. Then you can determine a lot of properties up to some high accuracy. You can't determine every energy eigenstate, but if you just average over a very tiny window, you can determine everything exactly. So that's the remarkable thing, that if these numbers are statistically independent of each other, then you can solve the problem in the limit of a large system. So there's some kind of central limit theorem, and the system actually self-averages. So in fact, you don't even need to know what the numbers are. It's the same for every set of numbers, as long as they're independent of each other. And every site is statistically the same as every other site, and you would get, even for one sample, you would get the same answer. It's self-averaging. This is very, very different from something like Anderson localization, where everything depends on what the disorder is. This is like almost the exact opposite of that kind of physics. All right, so that's the picture, and here's some equations. If you want to see them in second quantized form, exactly what I've just told you in pictures. You have some set of U alpha, beta, gamma, delta. They're uncorrelated with each other, and there's only one number, energy scale I need to know, which is the mean square value, U, of these set of statistically independent numbers. There's also a conserved quantity, which is the density of electrons, Q, which goes between 0 and 1. And so you can now ask about the properties of the system for certain filling. The most interesting filling is Q equals 1/2, where roughly about half the sites are occupied. Okay, so this particular model, there's been a huge amount of analytical and numerical work in the past, especially in the past 5-10 years. And I think we can say quite safely we fully understand it. I won't go through, this being a colloquium, all the methods. I'll just state some of the results that we now understand about this model of interacting particles. So first of all, you can prove that there are no quasiparticles. It has a ground state with some gapless sets of excitations. And the relaxation time, if you perturb it, is in fact the Planckian time. This seemingly lower bound is saturated by this model. If you compute the Green's function, it has some power law of frequency or temperature, and then this scaling form, which is just telling you that the characteristic time is h bar over kt. So this is, if you think about this is quite remarkable. If you take any other system with quasiparticle, you ask, how long does it take to equilibrate? Or, if you perturb it a little bit. Well, surely that depends on the strength of the interaction between the electrons. So there's some energy scale determined, fundamental energy scale of the interaction, the value of that should come in, some J or U as we call it. But here, it doesn't matter. It doesn't matter what the value of U is. It could be anything. As long as the temperature is below U, the dynamical scale is independent of U. It's just determined by temperature itself, as in some of those experiments I showed you. So that's exciting, and some of this we knew already 20 years ago. Another thing we knew, and I'll give the references in a minute, it has a rather bizarre property, which we now understand very well, but was very confusing to us in the early days. So if you look at the entropy at a given temperature, now the entropy in almost any many-body system, as you lower the temperature, the entropy density vanishes. That is, the entropy divided by the volume of the number of particles goes to 0 as temperature goes to 0. Here, that's not the case. So if you look at the entropy divided by the number of particles, it turns out to be actually a universal number at Q equals 1/2, and we know this number precisely. So, and this has also now been checked numerically. And this is very bizarre because, as I told you, the density of states is exponential of the entropy. And if the 0 temperature entropy is finite, this seems to suggest that there's an exponentially large number of degenerate ground states. That seems, with random numbers, how can you get degenerate ground state? So that's not true at all. You don't need degenerate ground state to have a finite 0 temperature entropy. So there's no violation of the third law of thermodynamics, in which these limits are taken in the opposite order. So what's going on? What is really the density of states at low energies of this model, and why is the entropy non-vanishing as temperature goes to 0? Okay, so this is now also extremely well understood and checked by numerical studies, and this is where the recent involvement of string theorists was crucial in understanding this behavior. So what you want to do is compute this density of states by the path integral of this SYK model. And it turns out that when you evaluate the path integral, as I can show in about an hour if I was giving a lecture in an advanced course, which I will spare you, you can rewrite that path integral after some clever manipulations that were first proposed by Kitaev and Maldacena and Stanford, in terms of a path integral of a time reparameterization mode. So you have this integral, which is in general the path integral or opposition of all the fermions. You can reduce that huge path integral to just a one-dimensional path integral of a function f of tau. And this f of tau you can think of as a reparameterization of the time that's experienced by the electron. And this, of course, very reminiscent of how a graviton is a fluctuation of a space-time metric. So that's where the connections to quantum gravity come in, as I'll make explicit later on. Anyway, so you can determine the action of this time reparameterization mode. Again, I'll spare you the details. So when the dust settles, this is the final answer that we know today. So there are 3 different factors here. Each come from rather different physics. There's this exponential factor here, which is precisely this S naught. So this is telling you that the density of states is e to the n S naught over kb down at 0 energy. But there's no delta function of energy next to it. There's this sinh square root of energy. This is the energy dependence. And this sinh square root of energy comes from 2-dimensional quantum gravity. That's kind of emergent in this model at low energies, and first obtained by Kortler et al. That's Steve Schenker's effort at Stanford. Yeah, okay. I'm sorry, I don't have, I'm not going to go into any of the details. This is the words that you just have to rely on me and claiming this is agreeing on this. And then there's a prefactor, 1 over n, which is independent of energy. And that actually is not universal. It really depends on the fact that I have an SYK model with 2-body interactions. And that leads to this 1 over n factor that we determined only recently. Okay, so that's a summary of the basic properties of the SYK model. Most importantly, it has no quasiparticles, and it has this relaxation time, which is h power over kt, both of which I was hoping it would have, so my hopes were realized. But then there were some surprises, which I certainly didn't anticipate in 1993. One was that there's an extensive entropy as temperature goes to 0. And then there's, now we know after 30 years later that the density of states has this form at low energies, which can also be checked with numerics. I should have shown some pictures of this with the numerics, but okay, it's just basically a density of state with a sinh squared of energy, which has a picture like that. I'll show a picture a bit later. All right, so that's a summary of the SYK model. And now I'll tell you what it tells us about various things in real life, some more real than others. Okay, and I don't have a time in front of me. Okay, that's the time. I have to end by 5, is that right? Yeah, okay, good. So I'm going to tell you about a very recent, as yet unpublished experiment from my colleagues Philip Kim and his student Laurel, sorry, name will come to me in a minute, on really trying to realize an SYK model in the lab. So this is based on a proposal by Marcel Franz and his collaborators. So they said the following. So what's peculiar about the SYK model as far as the real world is concerned is that it has random interactions between the electrons, but it doesn't allow the electrons to have any bandwidth. There's no hopping of single electrons. So how can we prohibit, have the single particle states all have exactly the same energy? Well, there's one easy way to do that, put them at a Landau level. So if you put all the electrons at a Landau level, you get a flat band. So once you have you need a flat band with lots of interactions. So they suggested taking a flake of graphene, and the randomness is just the edges, is the randomness there, and then putting it in a magnetic field, and looking at one of the Landau levels, and then maybe there'll be some physics associated with the SYK model there. All right, so this is a very wonderful suggestion, and so we started thinking about it. So we said, okay, suppose you were able to do this. Before I get there, let me show you the actual picture. Really, one of the first time this is being shown publicly by Laurel Anderson. I forgot that. Sorry, and Philip Kim. And this is an actual picture of the device. And there's a little flake of graphene, and then you have these two leads where you're going to measure various things across this device, and therefore understand something about what happens to electrons in a flat band with random interactions. You don't want to make the flake too large. If you make it too large, then the fact that there's something at the edges is not going to be that important. You'll just get a bulk property, which is relatively few interactions associated with it. Okay. So one of the things they measured, and they measured a lot of things. I'm only going to show you one set of measurements because we were really focused on this, as you'll see in a minute why. It's something called the thermopower. So they apply a temperature difference from the two leads. You put a delta T between these 2 points, and you measure the delta V. So you put a temperature difference, and you measure the voltage difference. So this is a thermoelectric effect, and the thermopower is the ratio of delta V over delta T. And the beautiful thing about this quantity, it's just given by dimensional analysis as the ratio of two fundamental constants, because you can see E times V is an energy and V times T is an energy. So then what's left over is just a pure number. So it's just a pure number which characterizes something about your many-body system. And what does it characterize? Well, it characterizes basically the particle-hole asymmetry. Because if positive charges and negative charges are equally likely to be thermally excited, then there won't be any voltage. So that's the fact that there's some particle-hole asymmetry, meaning that you cannot have Q equals 1/2, the Q has to be away from 1/2, then there will be a thermopower. All right, so theoretically we looked at this a few years ago. So here's a SYK model, and we coupled it very weakly to two leads and computed the thermopower. And what you find is that, just look at the last answer, it's given by this quantity, and this is really why we love the thermopower, because it's related to the derivative of the entropy with respect to charge. And so now, of course, the unique property of the SYK model is that the entropy doesn't vanish as temperature goes to 0. And so this derivative also won't vanish. So if you really had an SYK model, the thermopower is non-zero as temperature goes to 0. And that's actually very unique. There's no other system which has that property. But you do need a flat band for that to happen. And if you had a normal metal, and if you compute this, then you find that the thermopower is again ds dq, but since the entropy vanishes, the thermopower also vanishes linearly in this case as temperature goes to 0. So of course in the real system we don't have an SYK model. The point here is, of course, not to study the SYK model in the real system, because the SYK model we understand completely. The point here is to understand how wide is the domain of applicability of the SYK model. Could some other model, which is not precisely the SYK model, where the randomness is not truly independent, which maybe has a little bit of bandwidth also, can you get SYK lay physics there? And in this system, for example, you have 100 electrons. We have no way of answering that question other than by doing the experiment, because we have no way of solving such a large system on the computer with some random interactions on the edge. So we just do the measurement and then compare to what the SYK model does. Okay. Of course, we have to be a little bit more careful with the modeling. So let's imagine that in the modeling, in addition to having the random interaction, there's also some random hopping. And this has some mean square value h. This has a mean square value u. And this model can also be studied if these are independent random numbers. And from that, you find that there is a coherence temperature, which is of order h squared over u. And if you're below the coherence temperature, you get the thermal power vanishing linearly with temperature. And above the coherence temperature, you will get the SYK physics. Okay, so this is something that has been understood over the years. All right, so now finally I can show you some actual data. So that looks really quite a mess, but it in fact has a lot of structure which we are still analyzing, but looks quite encouraging. So what's plotted here is the thermal power as a function of the backgate voltage, which is some measure of the density of electrons. And as you change the density of electrons, there's a bunch of Landau levels. You're going to occupy different Landau levels. And so you really focus on one region, say this one, which is one particular Landau level with a single flat band, and you're seeing some physics there. You see lots of curves there. These are curves at different temperature, with blue being cold and yellow or red being hot. So one of the first things you see, just by looking at it, that at low temperature, the data is extremely noisy. And this is not random noise, this is reproducible noise. If you did the experiment tomorrow, you'll see the same. So it really depends on the detailed shape of the sample, exactly how you made the flake. You'll get one particular fingerprint in the noise. But as you go to higher temperatures, the noise disappears. And this is kind of made more quantitative in this plot. Then you can also look at the average values. If you look at the average value within a given Landau level, you get exactly what you sort of expected from the SYK model, some regime of temperature-independent behavior, and then it vanishes linear in temperature. So there's a coherence temperature here. I don't have my glasses. Of between 5 and 10 Kelvin. Okay, so that looks great. But the surprise, which in the end really wasn't a surprise if we had thought about it a bit, why is this fingerprint fluctuations, why are they so much larger in the Boltzmann-like normal metal regime than in the SYK regime? And that's actually quite easy to understand when you think about it, because in the single quasiparticle regime, you're averaging over the properties of n quantum states. There's the n quantum states available to a single particle. There's some set of levels near the Fermi level that are most important, and they only have like n states to explore. So as you change the Fermi level, you're really exploring different of these n states. On the other hand, if you don't have quasiparticles, your Hilbert space is much larger. It's e to the n, or 2 to the n. It's not n. So there's a much stronger self-averaging happening, and you don't see any dependence on the shape of the sample, or much weaker. Anyway, so this is something you can make quantitative. So the striking feature of observation of finite n is a fluctuation from randomness, depending on exactly which particular edge sample you have, are much larger in the normal metal regime than in the possible SYK regime. And so, for example, you can compute in the normal metal regime. This is in fact an old problem for the conductivity, for example. You can compute it. And this is connected to this phenomenon called universal conductance fluctuations. And you find that it diverges as temperature goes to 0 as 1 over temperature squared and 1 over n squared prefactor here. And this is intimately connected to the repulsion between the single particle eigenstates. Okay, so it's really random matrix theory of single particle states. But if you're on the SYK regime, you don't actually have access to the many particle eigenstates, because the operator, you're injecting single electron, that is not a matrix element between the many particle states. It's really changing the many particle state in a small regime. Because the successive many particle states are completely different from each other. They don't differ from each other by the occupation of just a single electron. So as a consequence, the fluctuations in the SYK regime are much weaker, they're finite as temperature goes to 0, and in fact fall off as 1 over n to the 4. All right, so at least qualitatively, this is by no means a proof. We can still hold out hope that this graphene flake is seeing some of the physics of the idealized SYK model. Many of the qualitative features are exactly what you expect. And hopefully, with further experiments, we can make a more quantitative test of these things and more theory. All right, okay. So I'm done with topic number 1. I've told you about the SYK model and how it's a many-body system with no quasi-particle excitations. Then there's a toy model. There's a recent beautiful experiment by Philip Kim and Laurel Anderson, which, may be in some sort of regime like that. So that's, ongoing work. But now what does this tell us about the other things in my title? So now I'm going to jump ahead to the theory of quantum theory of black holes. So let me try and give you in a few minutes some new facts about quantum black holes that have only come to light in the last few years. So what is a black hole? A black hole is a solution of Einstein's classical Einstein equations of gravity. And it's a solution where there's a horizon. So a black hole of mass m, the radius of the horizon is given by this Schwarzschild formula, where g is Newton's constant and c is the velocity of light. There's no h bar anywhere. And any beam of light or anything else inside the horizon will never escape because of the gravitational pull, since the matter inside the black hole is so dense. So in principle, any matter can form a black hole, but this requires you to compress it an incredible amount. You'd have to compress the Earth to the size of a pea to make it into a black hole. All right, so now of course we know there's lots of black holes out there, including one at the center of our galaxy. So this is one of the most amazing predictions of Einstein's theory of general relativity. But now you can ask, what is really inside a black hole? Well, in Einstein's theory, the matter in the black hole, it continues to gravitate once it goes past the horizon, and really it would collapse to a singular point. So there's a singularity in the classical theory at the center of a black hole, which is presumably why Einstein himself was skeptical when Schwarzschild showed him this type of solution, that there's anything to do with the real world. Anyway, we now know from experiments it does, but when you make matter so dense, you really have to worry about quantum mechanics. You can't just treat it in Einstein's gravity equations. So to really understand what's inside a black hole, you need quantum mechanics. You need to unify quantum mechanics with gravity. And that's a problem that many smart people have been working on for a long time, nearly a century. And a lot of progress has been made, especially in the context of string theory. Okay, but I want to now jump ahead to another fundamental fact about black holes, where you combine quantum mechanics with Einstein's general relativity, discovered by Bekenstein and made much more precise by Hawking. So imagine you have two entangled qubits, say these two electrons that spin in a half, forming this state, and you separated them. But you separate them across the horizon of a black hole. So one qubit is inside a black hole and the other one is outside. Now there's nothing funny happening at the black hole horizon. It's just some global feature. If you were falling through the horizon, you would never know you're falling through a horizon until you hit the singularity. So this entanglement must still be preserved. The inside of a black hole is connected to the outside of a black hole by entanglement. It's what quantum mechanics says. But if you're an observer sitting outside the black hole, and you have this qubit with you, you have really no easy way of finding out what the other qubit is doing. So if you're Alice out here, Bob inside the black hole can never tell you what the direction of that qubit is. So Alice would conclude that this qubit is just random. And this was partly well, not this particular reasoning, but this is the reason why black holes have a temperature and an entropy. Because to you, to Alice outside the black hole, the state of the inside cannot be known, and so this is really a random state. And randomness, as Boltzmann taught us, is entropy and temperature. So there is a black hole, and black holes have a temperature and an horizon. Black hole horizons have a temperature and an entropy, excuse me. All right, so Hawking, however, even did much more than that. He computed the value of the entropy and the temperature. And the way he did it seems, one of the ways he did it seems very suspicious that people were not at all sure it was right, but I think nobody doubts that it's right today. So he takes the path integral over the space-time metric of the action of gravity, in this case electromagnetism if you want. So this is what Feynman tells us you should do. You take the classical theory, get its action, and then you do a path integral over all possible configurations. And here the dynamic degrees of freedom are just the metric, and so you do this path integral. Now this is an impossible task. Even today nobody can do this path integral for a 3+1 dimensional black hole. But Hawking said, well, let me just take the saddle point value, because there's a 1 over h bar here, so I just approximate this path integral by the saddle point. And that's a very quick summary of some very brilliant work. And from this, and this computation of the saddle point outside a black hole. Now, you do this computation in Euclidean time, and it turns out that Euclidean spacetime just ends at the horizon, so you don't even need to worry about what's happening inside. So see, this allowed Hawking to not even worry about what's inside the black hole. Just by looking at the outside path integral, he was able to get an answer, and the answer was independent of what was actually inside the black hole. Okay, so he gets an answer, which is the entropy as a function of temperature. But Boltzmann has told us that entropy is associated with an quantum density of states. And Hawking's computation doesn't give you anything about what the quantum system is, whose density of states gives you this entropy. What are these states whose density of states is determining the entropy? And that's been one of the key problems that have been the focus of studies of quantum black holes. String theory has given an answer, which I'll mention a little bit in a few minutes. Okay, so from such computation, let me give you the explicit answers for a Schwarzschild black hole. This is the Hawking temperature given by the mass of the black hole. Has an entropy. It's proportional to the area of the black hole. But for further progress, one of the key facts that was important, certainly in my thinking, was the fact that if you now perturb a black hole a little bit, you can ask how long does it take to relax back to equilibrium. So imagine when you have, for example, two black holes inspiring each other, there's something called the ring down time. How long does it take for this to go from this shape to that shape? It turns out this is a very quick process for a black hole. This is just a property of Einstein's equation. And when you convert that in terms of temperature, the Hawking temperature is just h bar over the Hawking temperature. So amazingly, now this is the first inkling, and certainly it was for me, that there's a connection between black hole dynamics and non-quasiparticle dynamics. So if you want a quantum system whose density of states matches the entropy of a black hole, it better be a quantum system without quasiparticles. Because how else are you going to get this Planckian time in the real-time dynamics of it? Okay. Simple point, but really crucial. All right. So can we make progress with this? And so it turns out that for a Schwarzschild black hole, which is probably all the black holes in this universe, we still don't have a complete theory of what the density of states looks like. But for a charged black hole, a black hole with a net charge, amazingly we do now, or at least I claim we do. So we just take now another type of black hole where you have some net charge sitting inside in addition to a mass. So you have to take Maxwell's electrodynamics and Einstein's general relativity, and you look at the solution outside the horizon where in fact there's no matter nor charge. So it's just the vacuum Einstein-Maxwell equation which you solve, and you get a configuration called a Reisner-Nordstrom black hole. So if you look at the space-time outside a charged black hole, it has some rather peculiar features. So if you zoom, so there's a coordinate zeta, and you zoom into the horizon, what you find near the horizon, right outside, that the angular direction decouples. So in other words, this means you can take the angular fluctuations along the direction x and write them in angular momentum modes. L equals 0, L equals 1, and so on, just like you can do for earthquakes of the Earth. Normally, these are all coupled to radial fluctuations in the Schwarzschild black hole. But for a charged black hole, these angular fluctuations completely decouple, and you only have to take the L equals 0 mode into account. So now life has become very simple. You have a theory in one space, zeta, and time. You have to look at a black hole at low energies. For a charged black hole, a remarkable feature and a robust feature of the Einstein equations is that space-time decouples into a radial space-time with zeta and tau, and an angular part which you can just ignore, which only determines certain prefactors, which I'll come to in a minute. All right, so you get a quantum theory of gravity in one space and one time dimensions. Okay, now gravity in one space and one time seems almost trivial, but it does have black holes under certain conditions, and you can now make progress. So this is what many people have worked on, and so you can look at the path integral in one space and one time directions. And amazingly, this path integral of quantum gravity in one space and one time direction turns out to be exactly the path integral that I got for time reparameterization for the SYK model. It's literally exactly the same form, and you can derive it. So you can derive that same path integral in two ways. You can start with Einstein's equation and Maxwell's equations in 4 space-time dimensions and do this reduction to low energies. Or you can start from the SYK Hamiltonian I showed you and do its reduction to energy. You get the same path integral. Okay, if you want to know more, well, there's a review article in Reviews of Modern Physics that just came out that really shows you the both derivations and see how that happens. You get the same theory, and therefore, a somewhat tongue-in-cheek picture is that at least as far as certain feature of the density of states is concerned, the SYK model provides a quantum simulation of the states. It gives you the same features of the entropy that you have in the SYK model, but it also gives you more. It gives you a quantum system and gives you the full density of states that you can get on a computer and see that the formula works. Okay, so here's the actual result. So I remind you first, what was the density of states for the SYK model as a function of energy? It was this factor, this term here with 3 factors: the 0 temperature entropy, the cinch factor of square root of E, and then a prefactor that depended on some microscopic details. So now we know today that if a charged black hole, a generic charged black hole in any theory of gravity in asymptotically Minkowski 3+1 dimension, has the following density of states. And this is all expressed in terms of the area of the horizon at 0 temperature, which is related to Newton's constant, the total charge inside the black hole, velocity of light. So just one quantity A0 that characterizes the black hole. And the density of states as a function of energy, again, has 3 factors. The exponential factor is the Bekenstein-Hawking answer. And this is the analog of this factor here. Okay, so that depends only on the area of the horizon. And then there's a cinch square root of energy. There's no degeneracy. So here's an actual plot of the density of states of the SYK model, which can fit the cinch square root of E. I should really put this also earlier. So exactly like the SYK model, we have the cinch square root of energy. And then you have this prefactor. So this was obtained by Bekenstein-Hawking. This was followed from developments of the SYK model. So this is, quite an amazing fact. Amazing factor is one of the rare expressions you ever get that involves Planck's constant and Newton's constant in the same form, as was the Hawking result, but this even has another factor of h bar there. And finally, there's the pre-factor. This was only worked out recently by Eliasu, Murthy, and Turiachi. And this is really the only term that actually depends on what our universe is made of. It really is sensitive to the fact that we have photons in our universe and light neutrinos in our universe. You need to know the matter content, light matter content of our universe to get this power. And so it's quite a subtle calculation. It's not something you'll get from the SYK model, because the SYK model is only describing these two terms in a way, effect. Anyway, so that's a very beautiful result for the full energy and area dependence of the low energy density of states of a quantum black hole. Okay, with the net charge. And the charge is important because this dimensional decoupling only happens for charged black holes. Now, as I mentioned, string theory is also given earlier an answer, but the string theory calculation are also for charged black holes, so I'm not assuming anything that string theory also didn't. But they also assume much more. They assume low energy supersymmetry. Now, there may well be supersymmetry in our world at very high energies, but for a black hole, that's not important. What's important is what you assume at low energies. The SYK calculation didn't assume any supersymmetry, but you assume there's all the calculations in string theory assume there's supersymmetry, then you get a very different density of states. There's, of course, the Hawking factor, but there is, in fact, a delta function. This is a very peculiar thing. So the delta function means that the third law of thermodynamics is violated. There's some exponentially large degeneracy, and the coefficient of the delta function must be an integer. There's no such requirement for the generic black hole. And then there's a gap between the delta function, and these are the so-called BPS states and the high energy states. And even the form of this function is now well understood from an extension of the theory of the SYK model. And amazingly, if you take an SYK model and make it supersymmetric, this is exactly the structure that you get. All right, good. So that's, this little toy model has turned out to be a rather faithful representation of a certain sector of the dynamics of a charged black hole. That's, I think, and there's been a lot of progress in understanding now how information is preserved in an evaporating black hole, and a lot of it is built upon the calculations that gave you this result to begin with. Okay, so finally, I have a few more minutes. So I want to close the circle and get back to the original model, original problem in the cuprates that motivated the introduction of the SYK model. And so I'm going to talk about some recent work in collaboration, especially and led by Avishkar Patel, who's now at the Flak Institute. My current postdoc, graduate student, and postdoc soon going to Wisconsin, Ilya Esteles. And there was also an earlier paper by Avishkar with Ehud Altman that really set us thinking in this direction. So what we want to do is take this SYK model and have it describe not a little thing of graphene, but actually a bulk crystal, with infinite number of electrons. So the electrons are moving in 2 dimensions. So I really need a theory in 2 dimensions, not at a point. Theory at a point was sufficient for the graphene flake. It was apparently sufficient also for the center of the singularity of a black hole, but it's clearly not sufficient here. So we want to make this, take an SYK model and make it have a spatial structure. So what a lot of people did in the early days, 4 or 5 years ago, and including us, is take a lattice of SYK models and hook them up and try to see if you can reproduce and understand the experiment. There were many papers written, and it's very clear now you can't. You have to do some really absurd fine-tuning, and it doesn't work. So we want something that is much more reasonable. I think we have a way to do it. So we want to understand this strange metal, and we want to generalize the SYK model to something that has a spatial structure. So these are some of the properties we'd like to, I don't have time to go into any of the details. From all the experiments we know in the strange metal, as I've already told you, the resistivity is a linear function of temperature. It has a rather low value. The specific heat goes as T log T. The optical conductivity goes as 1 over omega with logarithms. And the photo emission gives you marginal Fermi liquid behavior. So don't worry, you'll just have to trust me that I'm telling you the truth. And these are various observables that essentially all strange metals obey. And we would like a theory that gets all 4. And of course, I'm showing you because in fact we think we have such a theory. And the correct starting point for this theory turns out not to be the SYK model. It turns out to be what people are now calling the Yukawa SYK model. And what is this model? Well, it's a model of not fermions with random interactions. It's a model of fermions and bosons with a random 3-body term, which are a Yukawa coupling. So here you have some fermions, in this case just dispersionless on some sites, and you have some oscillators phi with some label L, and there's this simple coupling, Yukawa coupling between the fermions and the boson, and you take this coupling and make it random. And in the large N limit, this particular model, which also only describes a point, it has no spatial structure, it has all the properties of the SYK model. I could have started with this. It's a historical accident that this is not how things happen. I could have presented at least the theory of the black hole starting from this model. It has all the same properties. Okay. All right, but now I want to make this have some spatial structure. So how do you do that? Well, this is what you have to do. First of all, you put the fermions and give them some kinetic energy, and then you have a Fermi surface. Okay. The bosons also move in 2 dimensions, and there's some mass term for the bosons, and I'm going to tune this mass term to be 0, so make the boson critical. This will involve tuning some, if the boson represents some broken symmetry, this involves tuning 1 parameter, and that's actually quite compatible with the many experiments. If the boson represents some gauge field or some emergent fractionalized excitation, then often this mass is not allowed by some symmetry, so you don't have to tune anything. Then you have a Yukawa coupling, and then you also put in some random potential. Now the key thing here is what depends on space. So this is a label. These couplings are in some fictitious orbital space, which we also have here, but I've suppressed the orbital indices. But we also now can imagine that the coupling, the Yukawa coupling, is a random function of space. In fact, the blue couplings are random, fixed random couplings in space, and the G is uniform in space. All right, so this particular model, without the blue terms, without the G prime term certainly, has been studied an enormous amount. And even for that, many of the results were not correct, as we've now worked out using our systematic SYK-based expansion. But I just don't have time to go into any of that. I'll just tell you what happens when you put in the G prime. So these are fixed random couplings, which are random as a function of position. All right, so this particular model, you can solve in an SYK-like large N limit. It gives you some kind of self-consistent Eliashberg equations, and you can solve them numerically or analytically in many cases and figure out what's going on. And what you find is exactly what you saw in the experiment. So first of all, if you look at the electron Green's function, you get a marginal Fermi liquid behavior with the inelastic scattering rate, which is linear function of frequency, and effective mass, which has a logarithmic divergence as a function of frequency. What's interesting is that both the G coupling and the G prime coupling give you this marginal Fermi liquid behavior. And the fact that the G coupling gives you the marginal Fermi liquid was known actually quite a bit earlier, in particular by Halpern and Reed. However, there's a huge difference, and this is the key to everything, between the times, the relaxation times you get in the electron Green's function than what you get in the transport. So the transport involves a more complicated computation, careful summation of these type of graphs, and when you do all that, you again do get linear frequency and temperature dependence in this transport scattering rate, and in the effective mass you get a logarithm. But now you notice that these singular terms, which is what's observed experimentally, don't depend on G. They only depend on G prime. So really the key thing is spatial randomness in the interactions, which was the key new feature of the SYK model too. Here this is generic, and we think it's really the key to understanding realistic strange metal physics, and the 4 properties I mentioned are fully reproduced by these results. Okay, it's exactly 5 o'clock, so I'll put up my summary. So first of all, I told you about the SYK model, which, like it or not, is at the very least we can all agree it's a solvable model of non-quasiparticle dynamics, and it's always good to have a solvable model to keep you honest. All right, so first I told you about experiments which literally try to get as close to possible to a real SYK model in the experiment. And graphene flakes seem to be doing a reasonable job. In particular, they show these universal conductance type fluctuations at low temperature, but at higher T regime, the fluctuations are much weaker, and they have a T-independent thermal power. And these last 2 things are exactly what you might expect from an SYK model. Then this is, of course, a big surprise. The SYK model captures the correct low-energy quantum theory of a generic charged black hole without supersymmetry. And so it gives you, one of the long-sought goals in quantum gravity, some quantum simulation of black hole microstates. And this is not to say there's actually an SYK model in our universe. Almost certainly not. But if you focus on low-energy sector, this is a good enough description. And then most recently, we've been trying to extend the SYK model to a realistic model of the linear T resistivity and other observed properties of the strange metal. And we find that it's rather generic and happens in any model in 2 dimensions, where you couple a metal 2-dimensional Fermi surface to some critical boson, provided the boson-fermion interaction has spatial randomness. Thank you.
So, any questions? Please. Yeah, please.
Can I ask?
Yeah, Bal, go ahead.
It's a very beautiful talk, very stimulating, I should
Thank
say.
you.
There is one problem I don't understand. Across the horizon, the direction of time changes.
Yes.
But if you are given a spinor, the spinor current defines a definite time orientation.
Okay.
So that is flipping across the horizon.
Yes.
And I am wondering how these spinor fields are globally defined. What is about? How do you match them? It has been a problem which has been bugging personally me for a long time.
Okay. Well, certainly all the calculations I described are in Euclidean time, where you have the cigar geometry, where the horizon with the space-time cuts off at the horizon. So everything is outside the horizon. So the gravitational calculation is completely done outside the horizon. Then you can take the SYK model and do a Euclidean calculation with it, and you get the same path integral, so you can then deduce what you want. Now, if you want to go to Euclidean Lorentzian time, where you go inside the black hole, that's very easy to do in the SYK model. You can solve it in real time, which we have done, and you get very complicated equations. Now, what happens to particles going across the horizon in ADS2? Okay, there are a lot of people studying it, but I'm not an expert on it. But my understanding it's all quite consistent. I mean, people are talking about wormholes that extend between black holes, and so they're really learning a lot from inside the black hole. But the structure of Lorentzian quantum gravity and its connection to the Lorentzian version of SYK model is not as well established, but it's clear you're getting the same physics.
Yeah.
So the Euclidean signature is completely established.
So in the same spirit, just I'll finish it off.
Yeah.
The action you're writing, the function that you're writing is over a distribution of densities. I mean, there are random variables which are getting integrated, like in the Anderson model. Okay. So the state defines on the algebra of observables is not pure; it's highly mixed. So,
Well, okay, so really this is a question of, if I look at this picture, so this picture is a histogram of the states of the SYK model. So really the spacing between this is a little bit of a coarse grain. If you look at the individual states, the spacing between them is e to the minus n, or it will be e to the minus 1 over g, okay? E to the minus, the inverse of this factor, which is gigantic, is the spacing between the individual energy levels. Now, if you want to know every single energy level, okay, that's something very, for an actual black hole, I don't know. Nobody knows what those are. That's, like solving a many-body chaotic system perfectly to exponential accuracy. But if I do even the slightest bit of coarse graining, just coarse grain, even over a window which is e to the minus 1/2 of this or something, then you get a very smooth function. It just self-averages. So, and that's a function I've shown you here. It's a little bit of coarse graining. And for the SYK model, you can test this numerically. When you coarse grain, it's independent of what you picked. It doesn't matter. The values of the couplings only depends the second moment, and that second moment determines this prefactor here. So this gamma here is the only thing that depends on the second moment of the couplings. For the black hole, you can actually figure out the couplings just by looking at the temperature and the entropy in the Reisner-Nordstrom solution that completely fixes this parameter.
Hello, sir. Very nice talk. I just want to ask the non-existent of quasi-particles in the SYK model.
Yeah.
Or as I understand, even if you have a hopping and you have all these random terms, there also you're getting similar behavior. Has it anything to do with the randomness of the interaction or something else? I mean, if I had...
Well, okay, that's a good question. So certainly there have been close to infinity papers for non-Fermi liquids without quasi-particles, without randomness. Starting with the paper Patrick Lee in 1989. That theory is perfectly okay. That is a system without quasi-particles. But when you compute its resistivity, it's not linear in T. In fact, the resistivity is 0. So those theories are Fermi liquid-like. So that's one of the peculiar properties I didn't have time to go into, which was at the heart of all the hard work we've been doing. You want something that not only doesn't have quasi-particles, but also has linear T resistivity. That has turned out to be much harder to achieve, but now that we have theory, it looks kind of obvious what you had to do. If you take interaction, only the G term, you can get a non-Fermi liquid and breakdown of quasi-particles, correct, but the transport looks like a Fermi liquid. Doesn't look any different. That's one of those,
okay.
You can't see that from the Boltzmann equation because you can't apply the Boltzmann equation.
Right.
Instead, you have to really do some careful summation of these what so-called Markey-Thompson and Islamazov-Larkin diagrams, and then you see that that's the case.
Right. So one more question I have. So suppose in let's say usual Hubbard model, if you make this U term, let's say random, or you take an extended Hubbard model and make the next nearest neighbor interaction random.
Yeah.
Will that also be a non-Fermi liquid behavior, or?
It will also be a strange metal. More than that, it could be a strange metal. So non-Fermi liquid I would define as something that doesn't have quasi-particles.
Right.
A strange metal is both a non-Fermi liquid and has linear T resistivity.
Yeah.
That's much harder.
Yes.
Actually, to come back to Bala's question on randomness. So in a real black hole, I'm sure there's no randomness. I don't believe there's some random set of theories that I have to study. But let's make an analogy to something like just single particle chaos. Suppose I take a quantum billiards. I have a particle moving in a billiard. There's no randomness there, but it has a very chaotic sequence of energy eigenvalues. If I want to predict every eigenvalue of a quantum billiards, I have to just solve the thing on a computer. But if I want to know something of the statistics of those eigenvalues, I can get them from random matrix theory. And that's the analog of what I'm doing. What makes this even sharper here is that the spacing between energy levels is really tiny, unlike quantum billiards, but just 1 over the system size. Here is exponential minus the system size.
Some of my friends have been looking very strongly at this ergodic behavior, this quantum chaos, classical chaos, like in the Sinai model, the classical chaos.
Sure, yes.
And how does it affect quantum theory?
Yes.
And from what I know, they are very perplexed. They don't know. Maybe you know some hints.
Well, so yes, you're right. So there's a hypothesis of Bohigas et al. That classical chaos implies random matrix statistics. I think for certain problems, there's almost a proof of that, but it's not well established. I agree. But here, the main point here is we're much, in some sense, it's because of this, we're looking at a quantum chaos in a many-body sense, which means that the energy level spacing is much, much, much smaller. It's exponentially smaller. So averaging over a few levels is not a big deal. Whereas if you have a real billiards, okay, then you can see individual levels. Here you can't, really. Nobody can see individual levels.
So in the last slide, you told about this non-Fermi liquid corrections entering into the specific heat, this temperature times log of 1/T.
Yes.
So it's also like similar situation for neutron stars, where you have this mini degenerate kind of states where this non-Fermi liquid states also appear. So I was wondering, like, this is like a leading order correction, and if you go beyond that, should it be rise to give some fractional powers or something like that in temperature?
Okay, so neutron stars, you meant black holes?
Not really. Like neutron stars having this degenerate, let's say, quark-gluon plasma inside that. So
Oh yes, so that's the different origin. That's in 3 dimensions. Yes. Yeah, so neutron stars with 3 quark-gluon plasma in 3 space-time dimension, and that does have a T log T specific heat.
Yes.
That's a different but related. This is due to randomness in 2 space-time dimensions.
Okay.
So it's related but not the same thing. Okay.
Okay. Sure.
Yeah.
Thanks.
They're both connected to absence of quasiparticles, but it's a different theory. Yeah.
So just a clarification. This 2 clarifications actually.
Yeah.
So in that graphene flake experiment.
Yeah.
So when T is greater than T coherence, you go into the SYK sort of. That's the
proposed.
Okay.
I have not claimed that they have done that. Yes.
So at least what's the picture? I mean, how does for T less than T coherence you have well-defined quasiparticles?
Yeah.
And everything.
Yeah.
Then as you increase your temperature, how does these quasiparticles die out? I mean, what happens? I mean, is there that?
Well, I think let's go the other way.
Okay.
So if you go to a high temperature, let's imagine that this U is much bigger than H and temperature is much bigger than H. Then I have an SYK model. So I have found something where I have a soup of system without quasiparticles. Now I'm cooling it. So naively you would say when the temperature becomes about H, I cannot neglect H. Amazingly, you can actually go to even lower temperatures before you have to worry about H. It only becomes important when you go to something that's about H squared over U. That's an even lower temperature. So the coherence temperature is quite low. That's really crucial. This factor of H squared over U is important. And where does that come from? Well, that comes from taking this critical state. So when you turn on the H, it's like a relevant perturbation. Eventually, it's going to grow and become important. So you have to ask how fast does it become important? You have to look at like the scaling dimension of this operator. And there's a 1/2 there that gives you this H squared. Okay. So the idea here is that when you go to very low temperatures, you've got these very big, heavy quasiparticles. So at short distances, there's no quasiparticles, but as you go bigger and bigger, suddenly they decide, okay, now it's fine, and this heavy thing will move together. So the quasiparticles are rather heavy. It's like a heavy Fermi liquid, but they're there. After a while, they just stop entangling with each other. So at short distance, they entangle, and then you get a quasiparticle.
Just a clarifying question. In the last slide, when we were talking about this boson that is coupled.
Yeah.
So when you do a replicated theory there.
Yes, of course I suppressed all of that.
Oh, yeah, okay.
Yes.
You do a replica. Okay.
But it's all replica diagonal.
It's a replica. Okay, fine.
So the point here is really the opposite of some of the things you were telling me of strong disorder fixed point. We're assuming that it's essentially a zero disorder fixed point. It could be eventually at really low temperatures, some of these strong disorder effects kick in, and we have to worry about things like the high-res criterion and all of that. but we are not there yet. In fact, Avishkar has been doing some numerical work to test all of that. Numerically, this seems to be perfectly valid down to some really low temperature. But ultimately, we will probably have to worry about some strong disorder effects here. Well, that's an interesting problem for the future. Especially some of your methods could be helpful.
Yeah, so thank you very much for the inspiring talk. I would like to return to the story of a graphene flake.
Yes.
So viewed from far away, in the language of some 40 years ago, this is a quantum dot.
Yes, yes.
So the SYK regime in such a quantum dot, is it something that the mesoscopics people knew all along back then?
This is one of the things they missed. they said there was this universal Hamiltonian quantum dot by Altshuler, where they said the only thing that matters was the average Coulomb interaction and an average exchange interaction, right? They missed the fact that there's the random fluctuation in U can also be important. So they didn't get this regime. This was the main thing they missed. But if you go to this low temperature regime here, where you're seeing all these fluctuations, this T less than T coherence, all of that work was in this regime, effectively. You can now put in a Coulomb blockade in the universal Hamiltonian. Here I'm assuming that's quite weak, but in our paper we have considered that case too, and modify, I mean, you can put it in both regimes and it changes things. But there is one regime where the random interaction dominates over everything else, and that was not a regime they studied. They could have, but they didn't.
And so does
we are studying it now. A lot of those people are working on that kind of stuff now. Yeah.
And so does it matter that it's a graphene flake, or it could be anything?
Could be anything.
So any generic quantum dot?
If we just want some generic system with some randomness, where the randomness here, the mean square value of this is smaller than the mean square value of that. That's what we want.
Thank you.
Sure.
Any more questions? Please.
Hey.
Hi, Peter.
Maybe a quick follow-up, Subir.
Sure.
On Rivaz's question. This is sort of trivial, but you said the obvious thing, which is that if I make the dot too big, the flake, then the randomness, you lose the randomness because some surface to volume argument.
Right.
On the other hand, if you want to test SYK, my understanding was you needed to go to large N.
Yeah.
So can you estimate for a real system where that crossover occurs and whether you should get correct answers or not?
Yeah, so, this system has N equals 100, and we cannot diagonalize a system of 100 electrons. Okay, so what you can do is, and this is something Alex Prof has a recent paper he's been working on. You can just take a flake with rough boundaries and compute the values of H alpha beta and U alpha beta and look at this second moments and look at their correlations and see if there is some reasonable SYK regime or not. If you take a too big a dot, then the mean value of this will become, the bandwidth due to this will become too large, and you won't have H much smaller than U. So I think, I don't know what the numbers are, but we haven't fully sorted that out. But that's a good point. That's something that needs to be studied more carefully. Yeah. But around this size, I mean, Alex has recent numerics, around the size of 100, 200 electrons, it does seem, at least we can say there's a regime where H is much, much smaller than U. When does that fail? And okay. And these results are literally, hot off the press, not yet written out. So, but I have the permission of the experimenters to show you.
Any other questions?
I have actually.
I'm sorry. So actually, if you take a really big dot and it's really pure, it could still be okay because you have a flat band. But then there's the physics of the criterion I was saying may not be quite right. But there'll be some other physics of a totally flat band that'll become more important. Yeah. Sorry. Go ahead.
About this analogy of the density of states with the SYK model and the black hole, I understand that the analogy with n is perfect. 1 over g goes to n.
Yeah, something like that.
But the entropy is the area. But the area goes with a different power. So do you understand why there is an enormous dimension or something?
Yeah, I mean, we kind of understand that, but it's really what you have to do. So you have, can I use the board here? Yeah, so let's see. So there's some path integral for the SYK model, which is df, which is a time parameterization of exponential. You have some S naught, and then you have exponential of some action. And the action is a prefactor, which is n times some gamma. And then there's a Schwartzian, as it's called, of f of tau. Okay, so the hard part is figuring out what is the number that appears here, and what is the number. So this is just a prefactor. So for the SYK model, we know the microscopic Hamiltonian. And from the microscopic Hamiltonian, we can compute this number exactly. There's an n here. Okay, so S naught is this transcendental number. That's my favorite number. Now, if you do the path integral of this is SYK, if you do Z for charged black hole, and you start from Einstein gravity, dg dA, of some action, this is the action of gravity, Einstein-Maxwell action of G and A. Then you do some dimensional reduction following Gibbons and Hawking, you end up with exponential of A over 4G, and you get exponential of exactly the same thing with some number here, which depends on G, and Schwartzian of f of tau. And it becomes integral over df. Okay, so you really have to do this dimensional reduction, which is what I worked out in painful detail. I think the string theorists knew this, but they were not be bothered to actually get the numbers. So I got the numbers. So you get some number here, and so you match that number, and it also has a 1 over g. So you match that with this, basically. Yeah, so it's just the low energy, so there's some effective field theory for the SYK model. The effective field theory is the same as that of the black hole. And now it's the parameters of the effective field theory, it depends on your UV physics. If your UV physics is the SYK model, then you get some number here. If the UV physics here, the UV physics of a 2-dimensional black hole is a 4-dimensional black hole. So you need to know how the 2 dimensions is embedded in 4. Now, if you want to go even higher UV, then probably string theory says you have to embed it in 10 dimensions. But those all turn out to be corrections that will be at higher energies. They don't matter at the bottom.
And just a final clarification on the UCAL SYK model.
Yeah.
Do you have a coherence temperature, as in the case of the flakes? What's that? In the sense that below that temperature, do you get superconductivity? Do you get superconductivity in that model?
You do, yeah. So there's a lot of beautiful stuff, especially look at this paper by Estes and Sharma. This theory actually has a superconducting phase, and you have a transition from a non-Fermi liquid to a superconductor. This is the dispersionless model. If you put a dispersion, then again there's a coherence temperature and so on. But in this more realistic model, you have to tune the mass of this to 0, basically, and then you cross over to a Fermi liquid. Yeah.
I think we'll close the session here. Any further questions can be discussed over tea. So let's thank Subir again for this wonderful talk.